Hello, can you hear me?
Yes, yes, I can hear you.
Yeah. And you can also see my screen, right?
Yes.
Okay, yeah. So it's recording. Great. Yeah. So let's welcome to the second lecture on randomized algorithms. So yesterday we saw the definition of a randomized algorithm, and we were looking at uh, we're looking at some facts from probability theory, but we weren't able to like complete the review of probability theory yesterday. So let's finish that today, and then we'll look at Las Vegas and Monte Carlo algorithms. Okay, yeah. So yesterday we talked about random variables, independent random variables, and the last thing we did was a linearity of expectation, and and that if x and y are two independent random variables, then the expected value of x y is the same as the expected value of x times the expected value of y. Okay, so now today we'll look at some facts about variance. So so we saw that expectation is linear, right? So now the question is variance linear as well? And so the linearity of expectation told us two things. Expected value of x plus y is the expected value of x times the expected value of x plus the expected value of y. And that for any constant alpha, uh, expected value of alpha x is alpha times the expected value of x. Now let's look at the analogous fact for variance. So we are given that alpha is in R, and we want to find out what variance of alpha times x looks like. Okay, so recall that yesterday we saw this alternative formula for variance. So it's expected value of alpha x the whole square. Right. Okay, so the first term I can write as okay. So in the second term, uh, I can bring out alpha common, alpha outside expectation, right? So I can write this as alpha. Now again, using linearity of expectation, so x square is a random variable and alpha square a constant, right? So using linearity of expectation, I can take alpha square out of the expectation. So I get alpha square. And this is alpha square times, this is just alpha square times the variance of x. So is this fine? So yesterday you were saying that you thought if you multiplied a variable with a constant, its expectation would become squared. So it's not the expectation, but the variance that becomes squared. So is this fine?
Yes, yes.
Yeah. Okay. So
Yeah, so even we can prove it in a slightly different way also. Like say the variance of the x is the expected value of x minus the mu whole square. So
right.
yeah, and mu is the average basically. So now I replace x by the alpha x and mu by the alpha mu. And then we can take the help of the linearity of the expectations, and then we'll get the same.
Right. Yes. Yeah. And okay. So this was sort of variance of alpha times x. Now we are also interested in variance of x plus y, right? So in general, variance of x plus y is not the same as variance of x plus variance of y. But so let's see a proof of this. And in the proof of this, we'll see that dependence is used crucially. Okay, yeah. So again, so I can expand the square out, right? So I can write, okay, so in the second term, expected value of xy can be written as expected value of x plus expected value of y using linearity of expectation, right? So now again, I can use the, okay, let me not do it now. Let me just copy this as it is. Yeah, let me just, yeah. Okay, so in the first term, I have now three random variables, right? X, uh, x square, 2xy, and y square. So I can say that this expectation is the sum of the expectation of x square plus the expectation of 2xy plus the expectation of y square, right? But again, in 2xy, I can, in the expectation of 2xy, I can take two outside expectation, right? So using linearity of expectation, I can say that this is, and I can expand this out. So yeah, so is this fine?
Yes, yes.
Yeah. Okay, so now what I can do is I can rewrite this thing as, so I expected value of x square from here and this from here minus, yes. So now what's this first bracket?
So this is the variance of x.
Yes, yeah. And the second one is variance of y, right?
Yes.
Okay, so I claim that these two are equal. So these two must somehow cancel out. But why do they cancel out?
Yes, because x and y are independent.
Right. And so this is, yeah. And in general, this term without the two is called the covariance. So covariance is expected value of xy minus the expected value of x, expected value of y. So what happens is that when they are independent, the covariance is zero, and so you get this variance of x plus y is variance of x plus variance of y. And in general, you would have a covariance term over here. So is this fine?
Yes, yes.
Yeah. So now let's look at some probability distributions.
So what is the interpretation of the covariance?
Okay, so what's the interpretation? Okay, first of all, what's the interpretation of variance? It's how much a variable is spread out, right?
Yes.
Yeah, so the covariance is how much the two variables vary together or vary in the opposite direction.
Okay. And how is this different from correlation then?
Okay, first of all, correlation. Okay, so the correlation coefficient always is always between -1 and 1, right?
Yes.
There is nothing like this for covariance.
Okay.
Yeah. Okay, so now let's look at some probability distribution. And we say that, okay, so we'll denote it by BRP. And we say that a variable x is distributed according to the Bernoulli distribution if x is in 0, comma 1. So script x, the domain of x is 0, comma 1. And the probability that x is 0 is 1 minus p. And the probability that x is 1 is p. And the expectation of the Bernoulli distribution is p. And the variance, okay, I should write variance like this. Yeah, and the variance is 1 minus p. P times 1 minus p, okay. Uh, yeah, the second distribution that we would need is the binomial distribution. And we say that, so the binomial distribution has two parameters, n and p. P determines the probability and n determines the range or the domain of the random variable. So we say that x is distributed according to the binomial distribution n comma p. If x lies in 0 to n, and the probability that n the probability that x equals I is n choose I, p, p to the n. Yeah, so what is the interpretation of this probability?
So it means that in the uh, say if it is equivalent of flipping a coin, then we
Hmm.
got say a success with the probability of say pi and failure with so in I flipping of the coin, we got, say, not in N flipping of the coin, we got success I times and the failure in minus I times.
Yes, yeah. And so, okay, um, uh, like another way to say that the same thing is that if x1 to xn are distributed according to the Bernoulli distribution and they're independent, so as you said, if you flip the coin n times, each and every individual coin flip is distributed according to the Bernoulli distribution, and this then denotes the probability that you got I heads and one minus n minus I tails, right?
Yes.
Yeah. Okay. So the expected. Okay. So from this, we can easily calculate the expected value in the variance, right? So by linearity of expectation, the expected value should be the expected value of x1 plus up to xn. But the linearity of expectation tells me that this is the expected value of x1 plus up to expected value of xn, which is n times p, right? And similarly for variance, because x1 to xn are independent, right?
Yes.
Yes. Yeah. And so let me also like throughout the course, I'll frequently use this term IID random variables. Let me also quickly define that. So we say that variables x1 to xn identically distributed. That is, they're independent and we pick them from the same distribution. So for example, over here, x1 to xn are IID. And a lot of random variables that we, a lot of like sets of random variables that we encounter in throughout the course would end up being IID. And that would simplify a lot of analysis for it.
So I have a query here
So
that it's
yeah.
okay if the expected value of the random variable x is equal to np, because in the binomial distribution, say, it's slightly difficult to understand. So how do I perceive it? Let's say since x1 to xn all are independent of one another, so therefore expected value of x is equal to np. And
Okay.
but then how did we get the value of the variance of x as np multiplied by 1 minus p?
Okay. So for the expectation, now I don't even need independence because I have linearity of expectation, right? So I can without even without using independence, I can say this is x1 plus xn, which is n.
Yes.
Okay. Now uh, let's go back to this, right? Variance of x plus y equals to variance of x plus variance of y if they are independent, right?
Yes.
Yeah. So in this case, all the individual coin flips are independent, right? X1 to xn are independent.
Yes.
Yeah. So I can say that this is because each and every individual variance is one p times one minus p, right? So is this fine?
Why individual variance is p and then multiplied by 1 minus p? Why so?
Uh, so I lost you. Can you repeat that?
Yes, so why the variance of an individual, say x1, is p into 1 minus p? Why so?
So that this that the variance of a Bernoulli distribution is p times one minus p. Okay, so let me also quickly do that. Uh,
So can we take the help of that formula, say variance of x is equal to expected of x square minus expected of x the whole square get this value.
Yeah, so that's will do it. Okay, so now we know what this is, right? This is going to be p squared. So what is this quantity then? So we saw yesterday that this is 0 times, okay, let me write it like this. So this we saw yesterday, right? That if I have a function and I want to take the expectation of that function, I can have that function over here and probably x equals x over here, right?
Yes.
Yeah, and this is going to be, so when x is 0, this is 0 times probably of 0, so that doesn't matter. And when this is 1, this is 1 times 1 minus p, right? So this thing is, yeah, and so I can, wait. Oh, no, 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 no. The probability that x is 1 is p, right? Probability x is 0 is 1 minus p. Yeah, so the probability that, uh, so the probability that x is 1 is p, right? So this is 0 times 1 minus p plus 1 times p. And so over here it's p minus p squared. And I can take p common, I get 1 minus.
So what if instead of taking x as 0 to 1, say, I take the random variable like say x is equal to minus 1 to 1?
Okay, so in that case, the variance would be minus 1. Okay, so in that case, the expectation would be 0, right? So this term vanishes. And this would be 1 times 1 minus p plus p. And the variance would be 1. Right? Did I get it right? So minus 1 square, 1 minus p plus 1 square p. Yeah. In that case, the variance would be 1.
Okay, okay, okay.
Okay, so, oh wait, the variance won't be 1. Yeah. Okay, so expected value of x is only 0 if p is half, right? So if p were not half, then this itself would be p plus minus 1 times 1 minus p. So this would be 2p minus 1. Yeah. Yeah, this would be 2. The expected value of x square would be 1. So the variance would be 2p.
Okay. Okay. Yes.
Your voice broke. Can you repeat it?
Yes, so yeah, so expected value is 1 with p and minus 1 with this thing. Yeah, expected value is 2p minus 1. So yes, and the
Right.
expected
Okay.
value
P minus
is
1
x.
squared because there is a square over here, right?
Yes.
Okay,
And
let's just work it.
let us calculate this value just to see that
Yeah.
what happens.
The second thing would be 2p minus 1 square. So now what is 0? Oh, minus 1 square times 1 minus p plus 1 square times p is equal to 1 minus p plus p. So this is 1. So variance is 1 minus 2p minus 1 the whole square. So this is 1 minus 4p square minus 2p plus 1. So this is 2p minus 4p square, 2p common, 1 minus. Yes, yeah. So is this fine?
Yeah, so this slightly, this is incorrect, I think. This is 1 minus 4p square and then minus 4p plus 1. I mean the square of the 2p minus 1 is.
Over here?
Yes, yes, yes. So 4p square is 1 and then minus 4p.
Oh, yeah, yeah.
And then this value came out to be 4 common, 4p and then 1 minus p.
Yeah.
So I guess that if we assume the value as 0 and 1, then the spread is of 1 and the square of the 1 is 1. And however, now in this case, minus 1 to 1, so the spread is 2. And
Yes,
therefore, we are getting the variance is 4 here.
sorry, that's squares.
Yes, yes.
Yeah.
It's clear, yeah.
Yeah. Okay, then, okay, so now let's get back to randomized algorithms. We'll see a bit more probability theory either in sort of this lecture or the next one. Okay, yeah, it's in the next one. Yeah, fine. Yeah, so now let's get back to randomized algorithms. So now we will look at the notion of the running time of a randomized algorithm. Okay. So before that, what is the running time of an algorithm? So we can define a function t. So for an algorithm A, we can define a function t from natural numbers to natural numbers, such that Tn is the maximum over all in or over all input x of length n of the number of steps of A in the execution of x. So what does T say? Fix any x and count the number of steps that x requires, uh, that A requires on x, right? And take the maximum of all of this for all n. So this is the maximum time it would require for any string of length n to be executed, right?
Yes, so yeah, it's okay.
Yeah. And so we'll call this function Tn is the running time of for on input n.
So is this possible that uh, the Tn may differ in the different iteration of the execution of the algorithm
Okay,
A?
so if A were if A were deterministic, then once you fix x, its output is fixed, right?
Yes.
Not only that, for a deterministic algorithm, once you fix x, its behavior is fixed, right?
Once I fix X, I could not hear this thing.
So once I fix x, the behavior of a deterministic algorithm is fixed, right? It cannot change.
Yes, yes, yes.
Yeah. So every time I execute A on x, if A is deterministic, I would end up running the algorithm for the same amount of time, right?
Yes.
Yeah. So for a deterministic algorithm, this is well defined. I can define it like this. Okay.
And yeah, so okay, okay. So we will
Yeah.
take the maximum value of the steps. This is so.
Right. Over any input of length. Like for example, for some inputs, so for example, think of a sorting algorithm.
Mhm.
If the array is already sorted, it might not take any time, right? It might just take a linear time. But if the array is not sorted, it might take order n square time.
Right, but in that case, we do think of the average space complexity.
Okay, so okay, average over what?
So average over best, average over worst, and average over all the values in between.
No, okay, so when you say that you are taking
There is some issue, audio issue at your end.
that,
Now it's okay. I could not hear you.
okay, yeah, okay, so think of t as so think of a function, let me call it f, which maps x to the number of steps in A's execution on f, right? So let me call this f of x.
Okay.
So now what you are saying is we consider the average case, right? So
Hmm.
now,
No, again, I could not hear you. I could only hear till the point that you said that, okay, I consider a function f of x, and the f of x gives the number of the steps,
right.
say,
So now that you are talking about the now you're talking about average running time, you are talking about average of f of x, right?
yes.
But over what?
So, yeah, so over the different values of the x.
X, right? So you are talking about average across the different values of the input, right?
Yes.
Okay, but what do? We fix an input and then look at it, right? So we do not say that we would pick the input randomly or something like that, right?
Mhm.
Okay, so it's possible. Let's say you write an algorithm, deploy it. It's possible that you always get the worst case outputs, right? So in that case, if you had taken the average of running time across inputs, you would be in trouble, right?
Mhm.
So it doesn't make much sense to take average over inputs.
Mhm.
So we would see, okay, so I think in this slide or in the next slide, we would see one notion of average running time, but that would be for randomized algorithms. Okay. So let me get back to this question when we get to that point. Okay. Otherwise, I will end up defining it now and we would do it twice. Okay.
Okay.
Yeah. So Tn is max of all the running times. So this is the worst case running time, but worse over the inputs, right?
Yes. So, yeah. So,
Yeah, go on.
yeah, so are you asking this question that suppose that A is a randomized algorithm, then on any input X, the number of steps in the A's execution on X depends on the value of X and the random value used in the algorithm?
Yes, yeah. Yeah. So for any n in n, what is Tn? Is it a fixed number?
No, this won't be a fixed number anymore because it will depend on the random values as well. So
Right.
there, this would be a function of, I mean, this will depend on the outcome of the random number generator.
Right. So this would be a random variable, right?
Yes, yes.
Yeah. And so here's where we would use random variables. And okay, so now we come to your question. And since this is a random variable, it makes sense to talk about its expectation, right?
Yes.
And this expected value is called the expected run. And this, okay, so like as we discussed yesterday, expectation is a measure. Okay, expectation is average, right?
Yes.
So this is the notion of average running time that you would end up using in the course. Okay,
Yes.
so for example, let's think of the quick sort algorithm, right? So if okay, I'm getting ahead of myself because I'll cover randomized quick sort next week. But in randomized quick sort, basically you pick the pivot element randomly, right?
Yes.
Now we know that in the worst case, if you end up picking a very bad pivot, then your algorithm would require order n square time, right?
Yes.
But we will argue that if you pick the pivot randomly,
Mhm.
then the expected value of the running time, where the expectation is over the randomness of the choice of pivots,
Mhm.
that would be n log n.
I could not understand this. That
Okay, so in randomized algorithm, in the randomized quicksort algorithm, what you would do is we would pick the pivot randomly. Okay,
yes.
now our running time would depend on our choice of the pivot, right?
Yes.
So running time is a function of the random choice of the pivot. Let's say if my choice of pivot were x, okay, x is inputs. Okay, so if I quantify my choice of pivots by y, then
Mhm.
the running time t of y would be a random variable of y, right?
Yes.
Random variable that depends on y, and so I can talk about the expected value of t of y,
Right.
right? And we will show that that expected value, which is the average value of t of y, would
Mhm.
be n log n.
Okay. Okay. Okay.
Yeah, and so then you would say that the average running time of quicksort is n log n, where the
Mhm.
average is taken not over the input x, but
Mhm.
the random choice of our pivot.
Right.
So let's say you write up a randomized quicksort algorithm, and
Mhm.
then you run it on any input x, right?
Mhm.
What does our guarantee tell you? It tells you that as long as you pick the pivots randomly, it
Mhm.
doesn't matter what the input was. On average, it would take order n log n time.
Okay. Okay.
So that is much more meaningful than doing it over the inputs, right? For example, if you pick the input as if you pick the pivot as the first element always, and the array is already sorted, then it's order n square, right?
Yes.
Yeah. And in that case, if the input is sorted, you are done, right? There is nothing you can do. It will always be order n square. However, in this case, even if the input is sorted, you would pick pivots randomly. So with so in expected,
Mhm.
instead of hoping that okay, we will take average over the inputs, hope the input is good, and then say it's an order n log n. What we are
Mhm.
doing over here is sort of taking matters into our own hands. Doesn't matter what the input is, we'll make random choices and still end up with an average end up with an algorithm which in the average case is order n log n. Is this fine?
Yes. Yes. I understood.
Yeah. Yeah. Okay. So now let's look at this. So since the running time of A, yeah, I just sort of mentioned it, but while discussing it, but let me go it again. So since the running time of A is a function of the random bits or numbers it picks, it would help us to have a fixed probability distribution on the random bits or numbers, right? So because then, so like while discussing randomized quicksort, we mentioned that the running time would be a random variable or which depends on the random choices of the input bits, right? The random bits and numbers. So if we knew the distribution of the random bits or numbers, it would be much more easier for us to argue or reason about t of the random variable t of one, right? And so
Yes.
what we'll assume say R1 to Rm, and that furthermore for all I in M, Ri is distributed along the binary distribution with probability, and that they are independent. So R1 to Rm are the only randomness of A, and they are IID random variables. So is this fine?
Yes, yes.
Yeah. And so we can think of R1 to Rm as the outcomes of independent coin tosses, right? And so sometimes throughout the course, I would like call R1 to Rm as the coin tosses of A and say that A has a random algorithm A is the ability to test toss for pair coins. Okay. So I'll sort of use the term randomness of A, random bits of A, random string of A, and coin tosses of A interchangeably. Yeah. And we'll also call R, the string R1 to Rn, as the random string of A. Sometimes I'll call these coin tosses, sometimes random strings, sometimes random bits, but yeah, they mean the same thing. And
Okay.
yeah, so okay, so as we discussed before, the output of a randomized algorithm depends on two things: the uh, input x and the random string r, right? So I can denote the output of A on input x with random string r as this function, right? A of x comma r, function of two things, x and r. So
Yes.
now over here I have fixed r, right?
Mhm.
So okay, the way I'm doing this is as follows. At the beginning, A picked r, and then it's just executing x on r, right?
Uh, this so what this x1 here is, because I could understand that
X is
this
the input.
yeah, so but then you said x1, because I could understand that this x is the input and then we are running this
X,
algorithm.
I didn't say x1, I said x on r.
Okay, okay, yeah, then it's fine.
Yeah, yeah. And like this is a comma, not x1.
Yes.
Yeah, so I would denote the output of A on input X and with randomness R by this. So over here, R is fixed, right?
Yes.
The question is AX comma R still random or is it fixed?
Okay, so if I fix the value of r, then this ax comma r would be fixed, because if x is already fixed and if the
Yes.
sequence of random bits is also fixed, so this will also be fixed.
Yeah. And so this is sort of like saying that, okay, have the random algorithm pick all the random bits it needs at the very beginning, fix them, and then execute it, right? So with this view, it becomes much more easier to reason about A, right?
Yes.
That's why we are adopting this view. And also, if A runs for time at most t, then the number of random bits it can pick is at most t, right? Because it would take at least one time step to pick a random bit.
Uh, okay. Okay. So can't we reuse the random bits?
Okay, so this is sort of doing it, right? So A depends on x comma r. So let's say
Yes.
I take random bits r1 to rt. This doesn't say that I only have to use r1 at the first time, r2 the second time, and so on, right?
Yes.
I could have used at the second instance, I could have used r1 and r2 both.
Mhm.
But this less than or equal to still holds, right? So this need not be equality, but this cannot be n cannot be more than t, right?
Yeah. Somehow this thing is not clear. That yeah, if a runs for the time t, then this what
Right.
this m here is, m is the number of what?
Random bits over here.
Okay. Oh, I see.
Yeah. So I'm assuming that the only randomness A uses is R1 to Rn. Okay.
Mhm.
So since it takes at least one instance of time to sample a random bit, if I
Mhm.
run for t time sets, I cannot sample more than t random bits, right?
Yes.
So we have a nice upper bound on the size of R.
Mhm.
Yeah. Okay. So Now that we have seen that the running time of a randomized algorithm is a random variable, let's look at two notions of e- efficiency of randomized algorithms. Okay. So before that, when do we say that a deterministic algorithm is efficient?
Yes, so if algorithm solves a problem in the reasonably good time, say in the
Right.
polynomial.
And by reasonably good time, we generally mean this, right?
Yes.
Some constancy independent of it. Yeah, so this has to be a fixed constant. It cannot depend on n. So something like 3. Regardless of what the value of n is, c remains fixed, right?
Yes.
And so throughout the course, I'll denote this by poly n. So we say that a deterministic algorithm is efficient when its running time is poly n. Okay. Now the question is this: does it make sense to say that Tn is poly n for a randomized algorithm?
Yes, so if we are using randomized algorithm,
Okay, so when we are using a randomized algorithm, what is Tn? Is it a number?
so the thing is that since in the randomized algorithm we are also taking R as the input along with the X, and whenever I write say of the order of n raised to the power c, so n usually the input size, I mean the size of X. But now
Yes.
since R is also included, and if I consider that R has been taken from a Bernoulli distribution, so total number of the binary bits possible would be say 2 raised to the power n kind of the thing. So
And
yeah,
only
so I
end up
mean
picking one of
these many different R are possible.
right. So that is the okay. So if you let's say that the algorithm runs for time t, right? Then you would end up picking only t many random bits. Sure. Totally like the total number of random strings possible is 2 to the t. But out in any run of the algorithm, you would only end up picking one of them, right?
Yes, yes,
Yeah.
yes. So that would be the function of the execution time itself. I mean, these many depends upon the how many times we execute the algorithm. So I think that I mean if that is fixed, then yes, that would be polynomial. If R is fixed, then that would be polynomial.
So, but okay. So what is Tn? Is it a fixed number or is it a random variable?
Oh, since it is a random variable, so if I need to think in terms of the average of the random variable kind of the thing.
That's one way that we would see. So
Yes.
my point over here is Tn is a it does
So
not make sense to say that Tn is
so
a
my
value
point.
with some probability, right?
Yes. So, but then I could not hear you then for the last few seconds. But I guess that you
Okay.
said that yeah. So for this R, so the expected value of the R would be equals to n multiplied by p, and p is equal to half kind of the thing. So therefore, the expected
No, no, no.
value of
So okay, we did not say that. Yeah. All I said over here was that Tn is a random variable, right?
yes.
And this is a fixed function. So
Mhm.
let's say this is NQ. So once I fix n, this value is fixed.
Yes.
Let's say this is NQ fixed. But T of 10 is a random variable, right?
Yes.
And what does it mean to say that a random variable equals to a fixed number? This can only happen with some probability, right?
Mhm.
So Tn is poly n. We can't write this. We'll have to write something like what is the probability that Tn is poly n,
Mhm.
right? So the thing is, okay, so the answer is because Tn is a random variable. So Tn equals order n to the c is a probabilistic event, right? So we need to say is equal to something. Is this clear? What's the issue?
Uh, yes, it's clear that yeah, the probability of Tn is equal to poly. But what
Yeah.
this probability is,
So I haven't. Okay, so this dash is okay. Let me say equals something. So far, we haven't talked about calculating this probability, and in fact, this would depend on the algorithm A.
okay,
For example, you can have an algorithm A so that for one random string R1, A runs for time n square, but for some other random string R2, it runs for time d to the n, 2 to the n, right?
okay, okay,
So
okay.
calculating this probability would depend on the exact behavior of the algorithm. But all I want to say over here is that uh, you cannot say that okay, Tn is something because Tn is a random variable, and so this doesn't make sense.
Yes.
Yeah. Okay, so this brings us to two notions of randomized algorithms, efficient randomized algorithms. The first one is called the Monte Carlo algorithm, and the second one is called the Las Vegas algorithm. So you were mentioning something about the expected running time. So that's the second thing, Las Vegas. So let's first look at Monte Carlo. It's study a different version of efficiency. Okay. So we say that a randomized algorithm A is an efficient Monte Carlo algorithm if for all n in n and all inputs x of length n and random strings r, A on input x with randomness r holds in time t equals poly n. So regardless of what random string you pick, A will always halt in poly time. However, Ax, R is allowed to produce the wrong output sometimes, and in particular, the probability that it produces the wrong output over R is 1 over 3. So what am I saying over here? To think of the random variable Tn, what I'm saying over here is that so Tn is going to have a domain, right? I'm saying over here that the domain of Tn looks like 0, 1, 2 up to poly n, some fixed polynomial function. Okay. The probability that it takes values more than poly n is 0. Is this fine?
Yes, except this fact that how to ensure that t is equal to poly of n, I mean max poly of n, and not exponential. Your video got freezed, and
Can you hear me?
now I can hear you. Yeah. So my question is that how to ensure that this t is poly of n. It is true that it produces the correct answer. Sometimes I mean it is allowed to make mistakes. Uh, but what this t is equal to poly of n here is? I mean how to ensure this?
Okay, so we don't have to ensure this.
Yeah.
The definition says that we can. Okay, so what the definition says is the following: we can think of a randomized algorithm A. Now, it is either an efficient Monte Carlo algorithm or it is not a efficient Monte Carlo algorithm, right?
Mhm.
If it is an efficient Monte Carlo algorithm, okay, or rather I should say it like this: it is an efficient Monte Carlo algorithm only if it
Mhm.
always falls in poly n time.
Okay. Okay.
So it's the behavior of A. You don't need to ensure it.
Mhm.
Yeah. And depending on this behavior, I am calling it an efficient Monte Carlo algorithm. Okay.
Yes.
Yeah. Is it fine now?
Yes. Yes.
Yeah. And okay, so we will see tomorrow as in lecture two, the planned lecture two, that there is nothing special about 1 over 3, and you could have replaced this with any other constant. Okay. And okay, so we'll discuss that later, but before that, let's define another notion of an efficient algorithm. And this is sort of what we were talking about, efficient in the average case. So we say that a randomized algorithm A is an efficient last biggest algorithm if for all n input x and random string r, ax comma r is always the correct output. So over here, ax comma r could be wrong. Over here, ax comma r always has to be correct. But for some r, a might run for a very long time. In particular, the only constraint that we put on the running time is this, that expectation over r of the running time is poly n. Okay,
Yes.
right. So we saw two notions of efficiency. One in which the algorithm always halted in poly time regardless of the choice of the random bits, but could be wrong sometimes. And another notion is that it will always be right, but for some very bad random strings, it can run for a very long time. However, we have to guarantee that in expectation. So on average, it would run for poly n time. Okay.
Yes, but then how is that possible that for some of the arts it is taking quite a long time, and still the
Hmm.
average of the time came out to be polynomial?
Okay. So let's say that for okay. So let's say that random strings are in 0, comma 1 to the n. So it only picks the size of the input is n, and it also picks only r n many random bits, right? And now suppose that for 0 to the n, all the way up to, okay, let me do this. So suppose this was the behavior of the algorithm that for one random string, it takes exponential time, but for every other random string, it runs in time n. Okay. So now what would be the expected running time? So what's the probability that I pick 0 to the n? It's this, right? Yeah. So is this calculation fine?
So this is one, and then n minus this calculation. I don't think it is okay. Uh, n minus this is n plus one. It's okay, but then minus n divided by two raised to the
Let's
power.
say what yeah.
Yes.
Okay.
So yeah, so if I divide this n divided by 2 raised to the power n would be quite a low number, very small.
Right. That since I'm just interested in upper bound in this, and this is
Yes,
negative, I can completely ignore it.
yes,
Right. So this is at most n plus 1, which is less than 2n, which is poly n, right?
yes,
So it's possible that for some very bad random strings, it might run for a very long time, and still the running time in expectation might be poly n.
yes, yes,
So an intuitive way of thinking about this is this, right? So a random variable can take very large values, but with very small probability, right?
yes.
So when you are taking average, you are weighing all of them according to their probability, right?
Mhm.
An expectation can be thought of as a weighted average over the domain of a random variable, where the weight of every value in the domain corresponds to its probability, right?
Mhm.
So if the probability is very small, the weight on the value is very small. So even if the value might be very large, because it's scaled down by the weight, its contribution to expectation might be very small.
Mhm.
So for example, over here, the value was very large, 2 to the n, right? But what was the weighting factor? It was 1 over 2 to the n, which itself is very small number, right? So this is very large, but this is very small. So they sort of cancel each other out. You get 1,
Mhm.
which is which is a reasonable number, right?
Yes.
Yeah. And compared to n, the contribution of everything else to the expectation, 1 is very small.
Right.
Yeah. Just because a random variable can take very large values does not mean uh, its expected value would be large, because those large values might be taken with very small probability, right?
Yes.
For
And
example, yeah, do you know of the Gaussian random variable?
yes.
It's okay. This was a terrible drawing. It takes something like this, right? So it
Yes.
can take value. Okay, it can take arbitrarily large values. Values
Mhm.
can become be arbitrarily close to infinity, right?
Yes.
But for very large values,
I could not hear this last time. I could hear that, yes. So Gaussian distribution has, I mean, would be touching infinite. It's okay. We take very large values. It's okay.
but for
Now,
very large values, the probability is very. Can you hear me?
now I can hear you. Actually, there was some issue.
Okay.
Actually, yeah, this audio issue happens. I mean, after some time, it frequently happens. Your video
Oh,
gets released, and then I cannot hear you
so I can try once
for some seconds.
in my iPad. I can try joining using my data and hope that if it's only my laptop, my Wi-Fi would work better. Oh, come on. Why are you updating this now? Okay, so it's updating my GoodNotes app. So how am I supposed to use that?
Okay, so I think this is the
Yeah.
end. This is the end of the lecture as well. And probably you would like to cover the rest of the things in the next lecture. You showed in the
Oh, so
message.
still, hello.
Yes, yes. Now I can hear
Okay, yeah,
you.
yeah. So what I was saying is we still have half an hour left.
Yes.
So this was the end of lecture one.
Okay. Okay.
Uh, yeah, not lecture two. So actually,
Okay.
we were supposed to start from here today.
Oh, all right. Yeah. Yeah. Fine.
Right. Okay, so can you see my screen or is it not visible?
I can see your screen, but it is blank.
Okay. Okay. Can you still not see my screen? Is it still black?
Yes, it is still blank.
Okay. So let me see. Let me try this. Stop sharing screen from my iPad, share my computer screen, and then share my iPad screen again. Maybe that way. Yeah. Okay. Why can't I share my computer screen? Okay. So now we don't see any screen, right?
So yeah, I can see your video in full screen, but not your screen. I mean,
Stop sharing everything now. Okay, fine. So now let me try to share and share. Okay, can you see my screen or can you still not see it?
no, I can only see your video. Probably you have not shared your screen yet.
I shared it. I don't know why it's not sharing. Let me Okay, so what I can do is I can leave on both my computer and iPad. You stay in the meeting so that the recording continues. Then I can try to reach on in both. Yeah, yeah. The recording is still on. Now join. Yeah, I don't see why I can see my screen. Oh, okay, fine.
Now your screen is visible. Yeah, visible now.
Yes. Yeah. Okay, yeah. So this it was supposed to be where we are supposed to have from today. But yeah. So far we have seen randomized algorithm, some probability theory, and the definitions of Las Vegas and Monte Carlo algorithms. And what we'll do now is look at some more probability theory and then use whatever we see over here to argue that the two notions of efficiency for randomized algorithms, that is an efficient Monte Carlo algorithm, an efficient Las Vegas algorithm, are equivalent, and we'll also see how to boost the success probability of a Monte Carlo algorithm. So recall that over here, there was this probability 1 over 3, right? So we are saying that it's fine if it fails with probability 1 over 3, but should run in polynomial time always. So what we'll see is that it doesn't matter, this 1 over 3 doesn't matter. You could replace it by anything like 1 over 2 or 1 over 99, and this would still be fine. Okay. So, but for that, we would need to like prove this and this. We would need uh, okay, we would not need what are called concentration inequalities. Okay. And what concentration inequalities allow us to argue is that with very high probability, the value of a random variable is close to its expected value. Okay. So what this is saying is that, yesterday we discussed that one interpretation of an expected value is you toss a, okay, you perform an experiment many times, the average value would be the expected value, right?
Yes.
But that doesn't tell you how many times were you close to the expected value, right? How,
Yes. But yeah.
yeah,
Quantification was
and
not.
huh?
Quantification was not there. That okay, it would
Right,
be close to the expected value, but not how many times.
yes. And what concentration inequalities allow us to do that is to say that, okay, with a good probability, you would be close to the expectation. Okay. So now let's look at the first and the simplest concentration inequality. It's called the Markov's inequality. And it says that let x be any random variable that takes values in 0, 1, 2, and so on. So it is integer value and it is always non-negative. Okay. Then for any constant c greater than 0, probability that x is greater than equals to c is upper bounded by expected value of x over c. Okay. So is the statement fine?
Yes. Yes.
Yeah. And the proof is this. So yeah, I'm still connected. Okay, let me write like this. So more x greater than equals to 0. So this is okay. So I'm going to split this sum into two parts. One is okay. Yeah. So can you hear me now? I think I lost connection for a while.
Yes. Okay.
Yeah. So is this split fine?
Yes. Yes.
Yeah. Okay. So now I want an upper bound on expected value of x. Okay. So oh wait, lower bound. Yeah. Okay. So I want to get something which is smaller than this. And the way I'll do it is so over here. X is between 0 and C, right? So what I can do is I can, in this sum, replace X by 0. So is this fine?
So yeah, but why to replace is x by 0 and then x by c?
Okay, and the reason will be clear in the next step because this thing is 0 plus. So now I can take C out common from the sum, right? So I get C times. Okay, so what is this probability? I'm subbing over all C which are at least, I'm subbing over all X which are at least CP probability of
Yes.
this
So
is
the probability of x is greater than or equals to c.
right. And so we have that expected value of X is greater than this or equal to this. So which is what we wanted to prove, right?
Yes.
Yeah. So is this fine?
Yes, but then so what could be the layman's interpretation of the Markov inequality?
What could be the
Layman's, I mean, so how would you define this Markov
okay, yeah.
inequality from
So another
layman's?
way of saying this is this, right? Suppose so I can write this inequality in this form as well, right?
Oh, I see. So how far I am from the expected, say if I am d steps away from the expected value, so what is the
Hmm.
probability of having more than d steps away from the average? And that would be
Yeah,
less than or equals to 1 by 2. Yeah, makes sense. Yeah.
sort of because only in one direction, right? This is not saying that so d times expected value of X is being away from the expectation in one direction, being greater than it, right? It could also be
Yes.
smaller than it. So this is not saying anything about being smaller.
Yes.
Yeah, but this is saying that okay, you can't be too larger than the expectation.
Yes.
Now let's look at another inequality, which, okay, so this was only telling you that you cannot be too larger than the expectation, but we want it to lie in some range around the expectation. Okay, so we want a statement of the following form. You can't be too larger than the expectation and you can't also be too smaller than the expectation. Okay,
Yes.
and that is obtained by Chebyshev's inequality. So that inequality says that let y be any integer valued random variable, then for any d greater than 0, probability that the expect probability that y minus expected value of y is greater than or equals to d is upper bounded by variance of y over d square. So a couple of things over here. The bound is two-sided, right? You can't be too large, you can't be too small, and this works for any integer valued random variable as opposed to a variable which is integer valued and is only non-negative. Okay, so these are the two differences between Markov's inequality and Chebyshev's inequality.
So I could not hear this thing that what's the difference in the in this Chebyshev and then the Markov one? Except that here we are working in both the directions.
Okay, so y is an any integer valued random variable, right?
Mhm.
Over here, x is any variable that takes integer values, but only for non-negative integers, right? So x cannot be negative.
Oh, I see.
Yeah. And that we crucially used over here, right? Because I was summing over x greater than equals to 0.
Mhm.
Yeah.
Yes.
Okay, so let's look at the proof of this. So let me check at the event first. So for us, the event whose probability we want to bound is this. Now, okay, whenever y minus expected value of y is greater than or equals to d, I can square on both sides and get that y minus, right. So whenever y minus expected value of y is absolute value is at least p, the square has to be at least p square, right?
Yes.
Now, I want to claim this. So does this claim make sense? Can you tell me why this is true?
So yeah,
So this tells us that whenever event E1 happens, E2 must happen, right?
yes. So because here I have the absolute value, and absolute value is greater than or equals to d. So this will imply that I cannot think of actually, but it makes sense to me. But I'm unable to think that. Yeah, I'm
Okay, so
unable.
okay, forget about these exact events. What I'm saying is this: let there be two events, E1 and E2, and
Yes,
suppose that that E1 implies E2. Okay,
yes,
then my claim is that probability E1 is less than equals to probability E2. This is a general claim.
so since whenever E1 occurs, then E2 is likely to occur. So therefore, the probability of, I mean, yes, probability of E2 would be higher than the probability of the E1 because this E2 will become more certain than E1.
Right. Okay, so what is this saying? This is saying that whenever E1 occurs, E2 must have occurred, right?
Yes.
But E2 might occur and E1 might not occur, right?
Hmm.
So okay, whenever E1 occurs, E2 occurs. So whenever you want to add something to the probability of E1, okay, so let's think of it like this. Okay, so let's say that E1 is the outcome of some random experiment, and whenever the outcome lies in E1, it also lies in E2, right?
Yes.
Hello.
Uh, yes, yes. To some extent, it is clear to me, but not completely.
Okay, so here's another way of looking at it. So let's say this is the space, this is E1, and this is E2. So when I
Hmm.
say that E1 implies E2, E1 has to be the smaller one, right? This is E1, this is E2,
Hmm.
right? Because even whenever E1 happens, E2 happens. So every point that lies inside E1 must lie inside E2 as well,
Yes, yes.
right? So now, what does probability of even tell you? Probability of even tells you of, okay, probability of E1 is the same as the probability of picking some point in this set E1, right?
Mm-hmm.
But whenever I pick a point in set E1, since every point in E1 lies in E2, I must have also picked a point in E2, right?
Mm-hmm.
So whenever, since this, so whenever a point contributes to the probability of E1, it also contributes to the probability of E2, right? So think of this as throwing darts. Whenever the
Mm-hmm.
dart lands inside E1, it also landed inside E2,
Mm-hmm.
right? So if a dart contributes to the probability of E1, it also contributes to the probability of E2. So the
Mm-hmm.
probability of E2 can only be larger. It cannot be smaller, right?
Yes. Yes.
Yeah. Is it fine now?
Yes. 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 It is fine.
Yeah. Okay, so we have this now. So since this is a square of a random variable, this is always going to be greater than zero. And is this fine?
Yes.
Yeah. So now what does Markov's inequality tell us?
That this would be the I mean, this probability of this thing, y minus expected value of y whole square is greater than or equals to d square would be less than or equals to the expected value of y minus, I mean, in fact, this would be the variance of y and divided by the
Yeah.
d square.
And this is what we wanted to prove, right?
Yes.
Yeah. And now, so, okay, so what does this tell us? This tells us that, okay, another way of writing this would have been, okay, hmm, one, two, three. Okay, okay, okay. Okay, so let me do it like this. Okay, so, okay, yeah. Okay, so what does this tell us? This, I can write this thing as, so so Chebyshev's inequality tells us that the probability that y lies outside this range, sorry, this should be less than equals to, Yeah, yeah, this is fine now. Yeah. So what? Okay, so the probability that okay, so if the absolute value lies is less than equals to d. Oh, so I've used less, so I should use strictly less to make it a complement. Okay. Okay, so this might okay, so this event and this event are complements of each other, right?
Which two events are continuing?
This and this. So what this is saying is this is at least D. This is saying this is at most. Those are the only two possibilities, right? Because this is a number,
Yes, yes.
right? And this is the same as this, and this is the same as this, right? So
Yes.
what Abhishek simply tells us is that with probability 1 minus variance of y over d square, y must lie in this range.
Okay.
Yeah, so it must lie in a range which is okay. So the middle of the range is expected value of y, and then
Mm,
it must lie in the interval of d around it, right?
yes.
There is a slightly even a better way of doing it. So let's say d is looks like m times. Okay, then this tells us that hmm, yeah, because variance of phi can be oh wait, it should be squared. Yeah, wait, did I make no, not square, square root. Okay, okay. So if sigma is the square root of variance, either what's the square root of variance called?
Standard deviation?
Right. So let d be m times the standard deviation. Then what Chebyshev's inequality tells us is that the probability that y does not lie in this range is at most 1 over m square, right? Sorry, 1 minus 1 over m square. So this has,
Yes.
oh, sorry, this has to be greater than equals to. Yeah, so over here is less than equals to. So this has to be greater than equals to. Because I subtracted both sides from 1, right?
Yes.
Is this fine?
Yes. Yes. Yes.
Right. So what Chebyshev's inequality tells us is the following. The probability that you are within m standard deviations of the expected value is at least this. And other, so the negation of this is the probability that you are m standard deviations away from the expected value is at most 1 over m square.
Yes.
Right. So this gives us a very nice sort of a picture, right? For example, let's say your expected value was here and your standard deviation was this. So let's say this is one standard deviation, two standard deviation, three standard deviation, four standard deviation, and so on, right? The probability drops by 1, 1 over 4, 1 over 9, 1 over 16, and so on.
Mhm.
Yeah. So this is like sort of the best interpretation of Chebyshev that I know of.
Yes. Yes.
Yeah. Okay. So, uh, okay, we are 6 minutes over time, but let me just talk about the last. concentration equality, and from next lecture we can start using it. Okay.
Sure.
So I won't prove this because the proof of this is complicated, but I'll just like give you the statement. So let x1 to xn be independent 0, 1 random variables. These conditions are very important, otherwise you can't use this. So let x1 to xn be independent 0, 1 random variables, and let x be their sum. Then for any delta in the range 0 to 1, probability that x is greater than equals to 1 plus delta times expected value of x is at most e to the minus delta square ex over 3. And sometimes, like since, yeah, this becomes very small if I write it as a power of e, I sometimes write this as the the exp of minus delta square x over 3. And so this was telling us that the probability that x is much larger than the expectation is not uh, is small, and this is saying that x is smaller than the expectation is small. So probability that x is less than equals to 1 minus delta times expected value of x is at most e to the minus delta square expected value over 2. Okay. So over here the bound was additive, right? Over here the bound is multiplicative. So is this difference clear?
Yes, to some extent, but not completely.
Okay, so what this is saying is, uh, so this is a fixed number, right? So this is something like expected value of 5 plus 3, expected value of 5 plus 3. So minus 3 over here and plus 3 over here, right?
Yes.
And what this is saying is, let's say delta was 0.1, then this is x. Okay, so this thing is 0.9 expected value of x, and this is 0 or 1.1 expected value of x.
Yes.
What here to get the range, you are adding something to expected value of y. But here, the scaling factor changes.
Mhm.
So this is multiplicative. So this is sort of relative, right? For example, this is fixed. Regardless of how large expected value of y is, this is fixed.
Mhm.
Over here, if the expected value of y was very large, then this would also be very large, right?
Yes.
So the range would become larger.
Yes.
Yeah. Over here, the range would remain fixed. So that's the difference between additive and multiplicative error.
Mhm. Mhm.
Yeah. And so let's see one quick example of this. So let's say that x1 to xn are distributed according to the Bernoulli distribution. Okay. Then x is distributed according to the binomial distribution. X is their sum, and expected
Mhm.
value of x is NP, right? So now, what is the probability that x minus expected value of x in text? Okay, let me do it like this. This would be much better. Uh, 1 over 10 root 10. Okay, maybe 10 over root 10. I missed. Okay, so what I'm interested in is what's the probability that x is 10 over root 10 away from the expectation. Okay,
Mhm.
so now this is the sum. Okay, yeah, so if the absolute value is larger, then either uh, x minus expected value of x must be larger than 10n, or the difference must be smaller than minus 10 over expected value of x, right?
Yes.
Yeah, okay, so now let me teach. And this is the sequence. So using I just so this so the first quantity is less than e to the minus 100 over. Okay, let me write it in the XP notation. So 10 over root n square is 100 over n times, or negative 100 over n times expected value of x is np. So for the first one, it's 1 over 3. Yeah. So this is at most 2 times. Let's and let yeah, and this is small, right? So is this fine?
Yes, I'll have to revisit this calculation again.
Yeah. So
But
like
but
okay,
by and large, we have understood the crux of it.
yeah. So what I was trying to show you is this that for a binomial random variable, the
Mhm.
probability that your order rooted away from the expectation is small,
Yes,
right?
yes,
So, for example, a binomial variable can take values from 0 to n. Let's say p is half, so n over 2 is the uh, expectation. Let's say this is n over 2 plus, and with high probability it lies over here in this range. And compared to this entire range, which is of order n, this is a very small range, right? Order
right,
root n.
yes,
Yeah, so this is like a very tight bound. Like it shows that it lies only with very high probability, it lies very close to the expectation.
yes, true.
So is this
And
fine?
yes, and our goal is to get the tight bound because quite possible that Markov may give a result, but then that bound would be, would be larger, and we are
Markov,
looking.
Mar- Markov won't even give you the result because it is just one-sided, right?
Yes.
So yeah, but you are right. Chebyshev might give you a result, but it
Mhm.
would be a weaker one.
Yes.
On the other hand, this result would be much better.
Right.
Yeah. Okay. And so we would use this inequality to boost the success probability of the Monte Carlo algorithm. But that
Okay.
will do next week.
Sure. So is it
Yeah.
possible for you to share these notes today only because yeah, I can
Okay.
review.
So ISSS is supposed to create that Moodle page, and then I'm supposed to upload everything over here. but they haven't done it yet. So what I can do is I can share whatever I have to, with you over email,
Oh, yes,
at least
sure.
for today. Yeah.
Yes.
And from
That is
next week, whenever they create it, I'll share it on that page.
sure.
Yeah. And hopefully by next week, we'll also be able to have some clarity on time.
Yes, yes, yes.
Yeah. So like once that's created, I can create a poll over there. And yeah, if known objects will change the time for Friday from 6 to 7:30.
Yes, because on Friday, so we have the session from 5 to 6.
Okay. Yeah. So okay, officially I can keep it from 6 to 7:30. But if
Yes,
you're 5 or so minutes late, I can just like record the recap in that time and then we can
yes,
start
sure,
with the extra content, right?
sure.
Because having something like 6:15 to 7:45 would be strange. So it's let's just keep it from 6 to 7:30 official.
Sure, sure, sure. No issue.
Yeah.
Thank you so very much.
Huh?
Thanks. Thank you so very
Okay.
much.
Yeah. Yeah.
Yeah, yeah. Bye bye.
Yeah. So I'll share this on email. Okay.
Sure, sure.
Yeah. Thanks. Bye.
Yeah. Bye.